Hello everyone! When you take a look around, you see that the motion of objects changes all the time. Describing motion and how it works is the first step in really understanding physics. But what makes everything move? The answer is simple: forces, voimat. As we start this lesson, I want you to consider what you already know about the topic. Why does a dropped ball fall downward? What makes moving objects stop? What have these words on this list got to do with motion? Two essentials to understand motion are force, voima, and acceleration, kiihtyvyys. Acceleration is the rate at which velocity changes, and force is the ability to produce acceleration. Whenever we make use of the forces that act on matter, we are employing mechanical laws to work for us. Classical mechanics, klassinen mekaniikka, describes the motion of objects from parts of machinery to star systems. Understanding forces helps us build machines and buildings. Isaac Newton, working at the end of the 17th century, made observations, modeled them mentally, and then expressed those models in mathematical terms. In that way, Newton made physics a mathematical science. Newton demonstrated that the entire universe is governed by the same laws. Newton's laws of motion and gravitation apply equally to everyday objects on Earth and to celestial bodies. Thanks to Newton's laws, engineers have been able to design amazing things. Newton first set out the definition of mass, massa. The mass of an object is basically the amount of matter it has in it. Newton was the first scientist to make a crucial distinction between mass and weight. On a smaller planet, Newton argued, our mass wouldn't change, but our weight would be less. Thanks to space flights, we take that difference for granted nowadays, but the idea was revolutionary for its time. All matter has mass. Mass, massa, and weight, paino, are connected, but they are not the same thing. While mass is a measure of how much matter an object has, weight is a measure of how strongly this mass is attracted by gravity to whatever celestial body object happens to be sitting on. The unit of mass is kilogram, having the unit symbol kg. In Finnish, kilogramma, kg. The International System of Units, or SI system, is based on 7 base units. The kilogram is one of them. The SI has an official status in most countries, including Finland. In classical mechanics, the movement of objects is predictable given the information about the mass of the object and the forces acting on it. Mass has only magnitude but not direction, thus mass is a scalar quantity, skalaalisuhde. A force has both magnitude and direction, making it a vector quantity, vektorisuhde. Visually, you see vectors drawn as arrows because an arrow has both a clear direction and a clear magnitude, the length of the arrow. The magnitude of a force is expressed in the SI unit called Newton, named after guess who? The symbol for Newton is N. When determining what happens when many forces act on the same object, it is necessary to know both the magnitude and the direction of all forces to calculate the result. You can add vectors together. When you do, you get a resultant vector. You get the resultant force, resultant in Finnish, by combining all the individual forces acting on the object. The resultant force is like the force that would alone produce the same acceleration as all those forces. We consider only the simplest examples. Forces acting in the same direction will add together. For example, a 60N force to the right and 30N force to the right gives a resultant force of 90N to the right. When forces point to opposite directions, they partially cancel each other out. Subtract the smaller force from the larger force. A 30N force to the right and 10N force to the left gives a net force of 20N to the right. While some forces are obvious, others are less easily seen. There are two broad categories of forces: those that act because of contact between two objects and those that act at a distance. Let's first look at some contact forces, kosketusvoimat. A contact force is any force acting between two objects which are touching each other. If two surfaces are not in contact, they can not exert a contact force on each other. Applied force occurs when a person or object directly applies force to another object, causing it to move. Tension, jännitysvoima, is a pulling force transmitted through a rope, string, wire or rod, when pulled from both ends. The higher the object is being pulled in opposite directions, the greater the tension is. When an elastic object, such as a coiled spring or rubber band, is stretched or compressed, it is displaced from its equilibrium position. As a result, it experiences a restoring force that tends to retract it back to its ordinary shape. This force is called the spring force, jousivoima. A surface, such as a table, exerts a support force called the normal force, tukivoima, on an object that is resting on it, like the book in the photo. The normal force prevents the surfaces from penetrating each other. In geometry, a normal is a line or vector that is perpendicular to a given object, forming a right angle to that object. The normal force is directed perpendicular to the two surfaces in contact. If the surface is flat, the normal force is in the opposite direction of the object's weight and has the same magnitude. The stronger the normal force, the stronger the force due to friction, kitka. Frictional force is a resistance to movement. The direction of friction is always opposite that of motion. Friction is caused by parts of the moving object rubbing against each other or its surroundings. It is partly caused by interactions between tiny irregularities in surfaces. On the microscopic level, friction is mostly due to electromagnetic interaction between the atoms at the contact surfaces. Air resistance, ilmanvastus, is the reason why objects fall at different speeds. When an object moves through air, the air particles hit the front of an object, causing it to slow down. The amount of air resistance an object experiences depends on its speed, its cross-sectional area, its shape, and the density of the air. A parachute works by increasing your air resistance as you fall. Next, let's discuss non-contact forces, etävoimat. Non-contact forces are forces that act between two objects that are placed at a distance from one another. A magnetic force is experienced by any magnetic material in a magnetic field. Electric force exists between charges. The most familiar non-contact force is gravity. Newton set out the formulation of gravity in his law of universal gravitation. It states that every particle in the universe that has mass attracts every other particle that has mass. This attraction is gravity, painovoima. Gravity is a tiny force. It is almost impossible to measure gravity between small objects, such as you and your laptop, because it is so weak. The force of gravity becomes significant around massive objects, such as the Earth. Every planetary body is surrounded by its own gravitational field. Forces make things move, but they can also hold them still. Bridges must be able to withstand several types of forces from all sorts of directions. They do that by balancing forces in some places with forces elsewhere. These can all be calculated using Newton's laws of motion. Newton's first law simply says that mass wants to continue doing what it's doing, whether it's at rest or in motion. If an object is moving, it will carry on doing so in a straight line, unless something pushes or pulls it to make a change in direction. When a car stops suddenly, the driver carries on moving forwards. With no seatbelt to stop the driver with the car, the driver flies free until stopped suddenly by impact on the windshield or something. The task of the seatbelt is to stop you with the car. The car crash triggers an airbag to inflate, and this spreads out the force of the impact and stops the driver from hitting the front window. You might falsely think that the natural state of matter is to be at rest. If you are driving and take your foot off the gas pedal, you might falsely think that as soon as you stop having the engine apply a force to the car, it stops. But, in fact, the friction generated by the car's tires making contact with the road causes this action. If you are in winter conditions on an icy road, the coefficient of static friction of your tires could go down to almost zero. If the curve is icy and you are traveling at too high speed, then what will happen? Remember that unless acted on by an external force, the natural state of matter is to continue on its initial straight line path indefinitely. This ball keeps moving a straight line once it's detached from the rope. The first law is also called the law of inertia, because the natural tendency of mass to preserve its present state of motion is called inertia, Hitaus. The mass of an object is really just a measurement of its inertia. Mass shows how much an object resists acceleration when it is pushed by some force. The more massive an object is, the more it wants to continue doing what it is doing, and the less likely it is to be deflected, slowed down, or sped up by an outside force. To get an object to move or otherwise change its current state of motion, you have to apply a force to overcome its inertia. Sumo wrestlers normally have a large mass. This is because the greater mass increases the effect of inertia. Heavier people are harder to move out of the ring. Try this at home. Place a paperclip or a coin on the card and place the card over the open end of a glass. With a sharp flick, hit the card out from under the paperclip or coin. What happens? The card will fly away while the paperclip or coin just drops straight into the glass. Why? Because of inertia, an object at rest tends to stay at rest. The paperclip or coin is heavier than the card, which means it doesn't move as easily. But once the card is no longer there to hold it up, gravity acts upon it and pulls it into the glass. According to Newton's second law, force is the thing that causes acceleration. In other words, force is the thing that speeds mass up or slows it down or changes an object's direction. The law describes how much force is required to achieve a given change in the velocity of a particular mass. The relationship between force and acceleration is given by this formula. It says that the force applied to an object is the product of the object's mass and its acceleration. Acceleration is the rate at which velocity changes with time. That is, how many meters per second the velocity changes every second. So, the unit of acceleration is meters per second. That is, meters per second squared. So, to use the formula, you need to use SI units, kilograms for mass and meters per second squared for acceleration. Because force is mass multiplied by acceleration, 1 Newton is the force needed to accelerate 1 kilogram of mass at the rate of 1 meter per second squared in the direction of the applied force. Put another way, the second law predicts the acceleration of mass when a given force is applied. According to Newton's second law, if the net force acting on the body is 0, the acceleration will also be 0. The simplest case of mechanical equilibrium occurs when two forces are equal in magnitude but opposite in direction. For example, an object on a level surface is pulled downward toward the center of the earth by the force of gravity. At the same time, a normal force is applied by the surface that resists the downward force with equal upward force. The situation produces 0 net force and hence no acceleration. According to Newton's third law, whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. This may sound as if it means that nothing will ever happen, but bear in mind, each force is acting on a different body. So, if you push something, it will be accelerated, but unless you are well anchored, you will also accelerate in the opposite direction. Forces exerting an equal and opposite force is the reason why many things work. When you row a boat, you push water backwards with the oars, and that makes the boat move the opposite way. Remember the third law when you step off a boat. To move yourself forward, you inevitably move the boat backward, and if you don't take that into account, you end up taking a swim. A rocket engine produces hot exhaust gases which flow out of the back of the engine. The third law gives an equal and opposite push forward on the engine. When your car is accelerating, it has to exert a force against the road, and the road has to exert the same force on your car. This reaction force on the car is what causes the car to accelerate. But shouldn't the ground accelerate in the opposite direction? Well, actually it kind of does. Your car pushes the Earth, affecting the motion of Earth. It is just that the Earth is about 6 trillion times. That means 6 followed by 21 zeros times as massive as your car. So the effects are so tiny, they are not noticeable. Newton's third law is a consequence of a more fundamental principle, the conservation of momentum, liikemäärän säilyminen. Momentum, liikemäärä, is the quantity of motion of an object. The International Space Station moves around the Earth in an orbit. The ISS is being pulled towards the Earth by gravity. It cannot escape. But why doesn't it plunge down to the Earth? Because it's moving so fast, it has enough angular momentum, moving it forwards and keeping it up. Angular momentum, pyörimismäärä, is a property of any rotating object. With a bit of a simplification, an object's angular momentum is the product of its mass, velocity, and distance from the point of rotation. The important fact about angular momentum is that it is conserved. It stays the same, unless acted upon by an external twisting force. Remember also Newton's first law. With no outside forces, a moving object will not stop. There is no air resistance in space, so once an object gets moving, there's nothing to slow it down. The law of conservation of angular momentum also applies to planets. The Sun and planets were born when a huge cloud of cold, swirling gas and dust collapsed under its own gravity. As this cloud began to collapse, it also began to rotate, so forming planets had some amount of angular momentum upon formation, and they are not losing it. Earth does not need any fuel to orbit the Sun. The combination of gravity and angular momentum will keep it doing so. Newton's laws are simple but powerfully accurate. In fact, they don't hold in all situations. They don't describe what happens when things are moving at close to speed of light or in strong gravitational fields. These laws are, anyway, all you need to describe how everyday objects move. I hope you are now familiar with these basic concepts. How would you explain these in your own words, as if you were teaching someone else? Thanks for watching. See you in the next video. Goodbye.